K1I is a fracture toughness. K1C is the material property, like yield stress, and can be determined by the different materials using standard testing methods. K1 is a microstructural sensitive property. The focus here is local crack tip regions and not global. As the case of Griffith's approach, all the restrictions or assumptions on K will apply to K1C. Okay, that materials are linear elastic behavior. That means no plastic deformation or other non-linear behaviors. Inverse square root singularity exists at the crack tip. And the K-dominant regions characterize the crack effect. So sigma xx is equal to Ki over f of theta over radical to 2 pi r. Fracture toughness K1C for some typical materials. For cast iron, it is 33. For low carbon steel, 77. For stainless steel, 220. For aluminum alloy, 24 T3, that is 33. Aluminum alloy of 75, T6, 28. For titanium aluminum alloy type, Ti6Al4V, 55. Inconel alloys of 600 or nickel-based alloy, it is 110. So we have already noted the fracture toughness is a microstructure sensitive property, and hence to get true values, the microstructure has to be specified. So this is referred from fracture mechanics, C.T. Sun and Z.H. Jern, Academic Press, Oxford 2012. So these values are taken from there. Is KIC really the material property like sigma y? Let's see what. So ideally, we would like to like KIC in mode 1 loading, and the K2C and the K3C will be the corresponding material property under other modes of the second third mode to be material property, independent of the geometry of the specimen. In reality, KIC depends on the specimen geometry and the loading conditions. The value of KIC is especially sensitive to the thickness of the material. Thickness, a thick specimen represents a state that is closer to the plane strain condition, which tends to suppress the plastic deformation and hence promotes the crack growth. And the experimental determination value of K1C will be lower for the body in the plane strain condition. On the other hand, if the specimen is thin, means the thickness is very small, okay, plastic deformation can take place and hence the measured K1C will be higher. In this case, if the extent of plastic deformation is larger than K1, will no longer be a parameter which characterize the crack tip accuracy. So here, thickness T of material also another factor. Okay. To use K1C as a design parameter, we have to use its conservative values. Hence, the minimum thickness is prescribed in the standard sample for the determination of fracture toughness. This implies that KIC is the value determined from plane strain tests. How do I understand the fracture criteria? First, one has to decide if the material is brittle or ductile. That is the first phase. If the crack tip is sharp or blunt. Okay, for the brittle it is sharp, for the ductile it is blunt. If the material is brittle, one has to decide the material is linear elastic or not. Again, another Whether it is linearly elastic or not is another case. For the linear elastic material, we can apply the concept of K and the material property Kc. Usually in the mode 1, this quantity becomes K1 and K1c. We would also use G and Gc, that is fracture energy. If the material is ductile, then we need to determine if the plastic zone is small compared to the K dominant zone. If yes, then we can continue to use the concept of K and the G. If the crack tip plasticity is larger, then we have to use the concept of the like J integral and CTOD or that delta function. The crack tip stress field in the case is given by the HRR fields, noting that technical JC is for the crack nucleation. Essentially, there are two approaches, global and local approach. Global is in the energy base and local is in the stress base, according to the English and these two scientists based on their work. For the linear elastic material, the energy and the stress field approach can be considered equivalent. Okay, so what is ductile fractures? In ductile materials, crack tip stress lead to plastic deformation at the crack tip, which further leads to crack tip blunting. Energy is consumed due to plastic deformation at the crack tip, which comes from elastic strain energy. This implies less energy is available for crack growth. Crack tip blunting leads to reduced stress amplification as the crack tip. Blunting will avoid stress singularity at the crack tip and may lead to maximum stress at certain distance from the crack tip. Okay, so crack tip blunting will lead to an increased resistance to crack propagation and increased fracture toughness. So we can see here here sigma YY for sharp crack tips. This is sharp crack tip, as we see. As we increase the crack length, the stress decrease and comes to down, which is a function of 1 over radical of R. When we come to here, maximum stress little ahead of the crack tip. This is the blunt tip. So it is not at here, it is just somewhere here. This is the point where maximum stress is, which is just ahead of the crack. So crack is here and the maximum is occurred here. And the graph shows that the blunted crack. So this is a schematic stress plot for blunted cracks and for the sharp cracks. Crack propagation in ductile material. In brittle material, the maximum crack opening stress or mode 1 is the crack tip ends, and hence crack propagation involves breaking of the bond at the crack tip. Sorry. So ductile material, I'll come back just for 1 minute. So in ductile material, the maximum of stress lies a little ahead of the crack tip, as we have discussed. So it is here. Okay, it is ahead of a crack tip. Crack tip is here. Here it is a blunt crack, and we can observe stress ahead of the crack. Okay, so in this scenario, the mechanism of crack changes. Okay, So void nucleate in the region of the high stress region, as so when we come here, it nucleates some void here on the regions of the maximum stress. So here we can observe void nucleation. Okay, so formation of void in the region of high tensile stress. Okay, the region between the void and the crack tip acts like a tensile specimen, and the microvoid formed in this region. Okay, so we can see in the region around here, we can observe microvoids. These are microvoids, formation of microvoids due to the formation of void in the region of high tensile stress. And crack extension occurs by the coalescence of the mic. So here we can see the coalescence of microvoids leading to the extension of the crack. So this is the coalescence of microvoids. So that leads to high crack in the material. What happened to a crack in the ductile material? So high magnitude of crack tip stress can cause yielding as a crack tip, plastic deforming that is. This leads to crack tip blunting, which reduces the stress amplification. There develops a zone ahead of the crack tip known as a processor. What else can happen at the crack tip due to high stress? High magnitudes of crack tip stress can cause a phase transmission. That is tetragonal to